Right, members. Now let's take back ourselves to physical chemistry, and here we come with solid liquid mixtures, solid liquid equilibrium mixtures, and particularly talking about eutectic mixtures. Sorry, eutectic mixtures or eutectic mixtures. Before we look at the definition, we need to first get the real background of how substances behave. Now, we're saying that when you get a liquid of a pure substance and you cool it, you reach a certain temperature where the liquid is converted to its solid at a constant temperature and pressure. Okay, you have cooled a certain liquid of a pure substance. Temperature is reached when that liquid is converted to its solid state at constant conditions of temperature and pressure. In that constant temperature at which the solid and liquid forms a pure substance, okay, the very constant temperature at which the solid and liquid forms, at which the solid and liquid forms of a pure substance are in equilibrium with each other is what we call the freezing point. So the freezing point of a substance is that constant temperature at which the solid and liquid forms of a pure substance are in equilibrium with each other. And we are going to realize that below the freezing point, the liquid will change completely to a solid. I'm going to consider an example of a cooling curve of molten lead. Molten lead is that lead that has been converted to liquid state, or lead in liquid state. The lead that is, maybe lead was heated and it got converted to liquid, so now it is cooling. Okay, so that's what I'm calling the cooling curve. Okay, cooling curve of lead. Let's consider a cooling curve of lead. We said that below the freezing point, the liquid will completely change into a solid. But what happens if we consider a cooling curve for lead? Molten lead. You have to bring in the aspect that it is in a liquid form. So this is temperature. So if I consider this cooling curve for molten lead, okay, moving it like that, along AB, you can see that along AB, molten lead is cooling, okay, as temperature decreases steadily. Temperature is dropping, and therefore molten lead is also cooling. Okay, so along AB, molten lead is cooling as temperature decreases steadily. As temperature decreases steadily. Then that is along AB. Along CD, see we have an equilibrium between molten lead and solid lead. and this occurs at constant temperature. That's why you see a constant temperature along CD. So along CD, an equilibrium is established between molten lead and solid lead, and this occurs at constant temperature. Okay, that occurs at constant temperature. Then from here, we have line BC at this, between here and here. So line BC this line BC, it shows a condition of supercooling. We call it supercooling. However, after forming the first crystal, heat is absorbed from the surrounding along this point, and further solidification occurs at constant temperature. So this BC shows supercooling, okay? But after formation of the first crystal, we are saying that heat is absorbed from the environment or from the surroundings, and further solidification occurs at constant temperature. Then point C, rather T, this point T is what we call the freezing point or the melting point of lead, because it is a temperature at which the solid and liquid are in equilibrium. We have to note that the freezing point of a liquid is depressed when another substance is added to it. And this always will depend on the relative amount of the substance or the solute added, implying that if we have molten lead, when it is cooling, okay, and you add something, okay, you have molten lead, it is cooling, and then you've added something to that cooling substance, or to the freezing substance, the freezing point will decrease, will be depressed. The freezing point will be depressed when we add another solute or another substance. Okay, and you're going to realize that the cooling curves for mixtures are obtained by varying each amount of each component in the mixture. And then you determine the temperature at which the mixture begins to freeze at each composition. Okay, and you are going to realize that the component with the higher composition solidifies out first. One can ask you to explain how cooling curves for mixtures are obtained. We are saying they're obtained by varying the amount of each component in a mixture and then determining the temperature at which the mixture begins to freeze. Okay, so this one is taking us to the real idea of what eutectic mixtures are. It is taking us to the real idea of what the eutectic mixtures are. Before we go to phase diagrams, we need to first bring out the background. We need to first bring the background of how or what eutectic mixtures are. We are going to have a lot of questions and a lot of information given. Now, members, consider cooling curve of liquid tin lead mixture containing 25% tin, and 75% lead by mass. Consider cooling curve of liquid tin lead mixture containing 25% tin and 75% lead by mass. When this liquid mixture is cooled, this liquid mixture is cooled at a fixed pressure, we shall reach a temperature T1 when solid lead. Why am I talking solid lead? Because it has a higher composition. Because it has a higher composition. Separates out of the mixture. And this temperature at which that happens is lower than the freezing point of molten lead. This temperature would be lower than the actual freezing point of molten lead. You first consider that. If you consider a liquid mixture containing 25% lead and 25%, rather 25% tin and 70% lead by mass, when it is cooled at fixed pressure and temperature, we have said that a temperature T1 is reached when solid lead separates out of the mixture. Why? Because it has a higher composition. Because we are saying that the component with the higher composition solidifies out of the mixture first. And this temperature has to be lower than the actual freezing point of molten lead. That one should be understood, because the moment we start phase diagrams for these eutectic mixtures, we shall be interested in all this information. Now, as this cooling is continued, as cooling is continued, okay, as cooling is continued, the crystallization of lead, because it's the one crystallizing out, the crystallization of lead makes the liquid mixture, less richer in lead until a certain composition where both components of the mixture solidify together at a fixed temperature T2. Very clear information. We are saying generally at first, lead separates out of the mixture because of its higher composition. And at temperature, we have said that it is lower than the actual freezing point of molten lead. But as the cooling is continued, the crystallization of lead makes the liquid mixture less richer in lead. Why less richer in lead? Because lead is being removed. Lead is crystallizing out. So the mixture is losing lead. It becomes less richer in lead until this one happens until a certain composition where both the components solidify together. They reach an extent whereby the composition of lead has become equal to the composition of tin, and as a result, they can both now solidify together at a fixed temperature that we are calling T2. So let me sketch this but this background this information is needed. This information is needed. A temperature is reached where both solidify. We are going to look at the definition of that temperature. Okay, we are going to look at the definition of that temperature and other information. So let's first sketch all this information on a graph and we see. We are having and here we have temperature, degrees Celsius. That is what we are having. So this one, let me call it T1, and I call this one T2. So, and I describe my points. Along AB, the liquid mixture is cooling. Okay. Liquid mixture. The liquid mixture is cooling. Along BC, lead is crystallizing out. Lead is crystallizing out of the mixture. Then along CD, both lead, because we say that it occurs along BC, lead is crystallizing at temperature T1. But along CD, that is at temperature T2, both lead and tin solidify or crystallize out together. Both lead and tin solidify or crystallize out together. Then along DE, now here we already have a solid here because the mixture is solidifying. So at CD, we have a solid mixture of tin and lead. But then along DE, also the solid mixture is still cooling. So along DE, the solid mixture The solid mixture is cooling. Then these points T1 and T2 are called, you can call them arrest points, or you can call them freezing points of lead. The first one is for lead, and the second one is for the mixture, because at T2 both lead and tin are solidifying. So, and mixture respectively. So that is what we are having. That is the summary of the other. Along AB, the mixture is cooling. But along BC, lead is cooling because it had the highest composition. But along CD, the composition is reached where both solidify at constant temperature. And along DE, the solid mixture is also solidified. The solid mixture is cooling. So here comes a question now. Before we define what eutectic mixtures are, here is a question. Explain how before I go to that, let's first define these terms. Let's first define these terms. Eutectic mixture. What is an eutectic mixture? What is an eutectic mixture? Now, an eutectic mixture can be defined in different ways. We can define it as a heterogeneous solid mixture. Heterogeneous solid mixture, heterogeneous solid mixture, which when heated, at constant pressure, will melt at constant temperature to give a liquid of the same composition, as the solid. I normally define this by using a simple mechanism. I define this by using a simple mechanism. We shall have another alternative definition, but you know, when I have solid mixture, I heat it, it melts. But melting takes place at constant temperature. When the substance melts, it gives a liquid. But that liquid should be of the same composition as the starting solid. So when I'm defining an eutectic mixture, now it can be easy for me. Heterogeneous solid mixture, which when heated melts at constant temperature to give or giving a liquid of the same composition as the solid. As simple as that. Heat a solid mixture, it will melt at constant temperature to give a liquid of same composition as the solid mixture heated. Or it can be a solid being heated to melt, or it can be a liquid mixture solidifying. Okay, if a solid is melting, then a liquid mixture should be solidifying. So one can still define it as a liquid mixture which at a constant temperature, which at constant pressure, solidifies. Now, a liquid is solidifying at constant temperature. Solidifies at constant temperature to form a heterogeneous solid of the same composition, as the liquid. Let's understand this mechanism also. For this case, you're having a liquid mixture now. You can have a liquid mixture. This liquid mixture will solidify. This one, heating takes place at constant pressure. Even solidifying takes place at constant pressure. At constant pressure, solidifies. When something solidifies, it forms a solid. So it solidifies from a heterogeneous solid, which heterogeneous solid must have the same composition as liquid. As simple as that. A liquid mixture, which at a constant pressure solidifies at constant temperature to form a heterogeneous solid of the same composition as the liquid. So this is what we call an eutectic mixture. Then we want to define that point at which these substances solidify. So we have what we call an eutectic point. So let's define what an eutectic point is. Eutectic point is a point at which two components of a liquid mixture solidify simultaneously all together without changing composition, without changing composition at a fixed temperature and pressure. Components of a liquid mixture solidify simultaneously without changing composition at fixed temperature and pressure. That point is what we call an eutectic point. Then we've got what we call an eutectic temperature. Eutectic temperature. For the case of an eutectic temperature, that is the constant temperature at which a liquid mixture solidifies, at a constant pressure to give a heterogeneous solid, a liquid solidifies to give a heterogeneous solid of the same composition as that of the liquid. Constant temperature at which a liquid mixture solidifies at constant pressure to give a heterogeneous solid of the same composition. Anything you're forming, there must not be composition. There must not be change in composition, sorry. There must not be change in composition. Now, let's look at conditions for the formation of eutectic mixtures. Conditions for the formation of eutectic mixtures. What makes this part very interesting is that the examining procedure keeps the same. Explanation of the phase diagrams is the same. So it's just a matter of understanding. So under what conditions do we form eutectic mixtures? We form eutectic mixtures when pure crystals of the components should separate from the mixture, on cooling. Pure crystals of the components should separate from the mixture on cooling. That's why we said that as the liquid is cooling, okay, the substance with the higher composition crystallizes out. It separates from the mixture on cooling, leaving out the other one with lower composition. The two substances involved must be completely miscible, when melted. The substances involved must be completely miscible. The components should separate on cooling. Those are the conditions. Now, we want to know, all these points I'm giving are examinable. So we want to see ways in which eutectic mixtures behave like pure metals or behave like compounds, okay? Ways in which eutectic mixtures behave like compounds or pure metals. In what ways do they behave as pure metals or as compounds? In the following ways. Both produce similar cooling curves. Both produce similar cooling curves. What else? Both have sharp melting points. Both have sharp melting points at fixed pressure. Both have sharp melting points at fixed pressure. Another one, they have a fixed composition. They have a fixed composition at constant pressure. Similar cooling curves, sharp melting points, fixed compositions. These are ways in which eutectic mixtures behave as pure metals. Now we want to see in which ways are they different. Let's see reasons why eutectics are not compounds. In some ways, they behave as compounds, but why are they not compounds then? They are not compounds because their composition vary with pressure. Their composition vary with pressure. Two, they are not compounds because they can be separated by physical means. They can be separated by physical means. That's why you call them mixtures, because if you remember from your senior 2 or senior 1, you defined a mixture and a compound. A compound cannot be separated by physical means, meaning it's not physically combined together. Components in the compound are not physically combined together. But for eutectic mixtures, since the components are physically combined together, then they can be separated by physical means. So they can be separated by physical means. Their composition will vary with pressure. Another one is their composition of an eutectic mixture doesn't correspond to any known compound. The composition of an eutectic mixture doesn't correspond to any known compound. For example, if we have like cadmium zinc mixture, this one forms an eutectic. You cannot be like the way you see. What I can tell that this is a combination of this and this and this, okay? And they can, once you mix these components, you can't separate them, but these ones can be separated together. So the composition of an eutectic mixture does not correspond to any known compound. Then another one is that microscopic examination. Microscopic examinations show that eutectics are heterogeneous. What do we mean? They are made of crystals of different substances. So these are reasons as to why eutectics do not why eutectics are not compounds. So those are the reasons. Now, we want to find out which tests were carried out on an eutectic mixture to show that it's not a pure compound. Because if this is the case that they are not pure compounds, what tests were carried out to clarify that? So tests that were carried out on an eutectic mixture to show that it is not a pure compound. Test number 1. Changing pressure. The test you can do is change the pressure. Let's say that can be. Changing pressure can change the pressure and see if the composition will change. Changing the pressure, you can change the pressure, which will change the composition of the mixture. Another test, you can do X-ray diffraction pattern. The X-ray diffraction pattern, they show the X-ray diffraction pattern that does not conform to that of a pure compound. Another one, we have the microscopic examination, which shows a heterogeneous mixture, of individual crystals of the pure components that make up the eutectic mixture. So these tests can be carried out to tell that eutectic mixtures really are not pure compounds. Now, in our next video, which will be the last lesson of this area, we're going to be looking at the phase diagrams, composition, the phase diagrams, how to construct those phase diagrams, and how to describe them. That will be in our next lesson. I wish you all the best for now. God bless you.